All right, so now we should summarize what we know about this thing. So maybe a theorem. So I suppose there was one more thing that was another ingredient that I should also perhaps include, and maybe I'll include it here. So maybe I'll say also for part 4, let's call it, say, y. What is y? Y is going to be the function. Okay. So this is y. What is that? It's the function that we've been talking about, the function y equals alpha x plus beta x squared, the quadratic function, which also best approximates all these three things. So we'll refer to the quadrants of curvature of that function at the origin, and also its quadratic curvature, radius of curvature, and so on. So all 4 objects get the same quantities, but since they're defined in terms of different kinds of objects, we should sort of connect these things. So for the, say for y, in terms of the r is, in terms of alpha and beta, 1 plus alpha squared cubed on 4 beta squared. The capital K is 4 beta squared over 1 plus alpha squared cubed. And the radius and the curvature are the obvious square roots. So little r will be the square root, will be 1 plus alpha squared over 2 beta. But we have to take a square root of this thing. So it'll actually be 1 plus alpha squared to the 3 halves, because there's a cube power there. And similarly, the curvature k will be, take the square root of this. So there'll be a 2 beta up on top and a 1 plus alpha squared to the 3 halves on the bottom. All right, so let's see if I can prove this. I can probably dispense with this diagram now. We've gotten that. So the proof. Well, we defined our quadrants of curvature right over here to be 4f squared plus g squared. And we have the alphas and betas in terms of the f's and g's. So what was that? The f in terms of alpha was alpha times 1 plus alpha squared over 4 beta. So we have to take all of that squared. And the g was 1 plus alpha squared on 4 beta. So we have to take the square of that. And what happens when we do that? Well, there's going to be a 1 plus alpha squared coming out of both sides. So there will be a 1 plus alpha squared coming out. But there will also be a 4 beta squared coming out. And then there will be an alpha squared plus a 1. That alpha squared plus 1 will combine with the other 2 to give us 3 of those 1 plus alpha squareds. And then when we take the 4 beta squareds out, then there'll be a 4 beta squared remaining, because the 4 squared is 16, which will cancel a little bit with that 4, giving us a 4 beta squared. Okay, so that's the formula for the quadrants. And then the curvature, the quadratic curvature, capital K is just the reciprocal of that. And these other ones are just the square roots of those. So in particular, as a consequence of that, we get a famous classical formula that goes back to the pioneers of the subject, back to Huygens and to Newton, who calculated with all this business. And this is a favorite topic for 17th and 18th century mathematicians. After Huygens introduced this idea of evolutes and, well, really curvature there. So the formula is that if we just think about alpha x plus beta x squared, and let's suppose that we do know a little bit of calculus for a second, all right, then we know that sort of as a function of x, y prime at 0 is just alpha. And y double prime of 0 is, well, you differentiate twice, you get the 2 coming down, and then you get 2 beta. So we can rewrite the curvature, little k, the curvature of this function at the origin. This is k at the origin is, well, where is it? Here's the formula right here. 1 plus no, here it is. 2 beta over 1 plus alpha squared to the 3/2. So the 2 beta is exactly the second derivative. So it's y double prime at 0 over 1 plus y prime 0 squared to the 3/2. Thanks very much, yes. All right, so that's a classical formula going back to Huygens and Newton. That allows us to calculate the curvature, actually, of any function if we have its Taylor coefficients, because the higher degree terms, not just for a parabola, the higher degree terms, x cubes, x to the 4th, and so on, they just don't matter. It's only the linear and quadratic terms that determine the curvature. Okay, now there's a corresponding theorem for the general conic. Of course, there's a little bit more involved. So the theorem, so this is now for this general conic Z. And maybe I should remind you that the conic that we're talking about is Lx plus my plus nx squared plus 2pxy plus qy squared equals 0. All right, so at the origin, the quadratic curvature is 4nm squared minus 2plm plus ql squared all squared over L squared plus M squared cubed. All right, so proof of that. Well, our formula for, let's say, the quadrants of curvature is 4f squared plus g squared. That was our defining formula. And so in terms of L's, M's, N's, P's, and Q's, we can write that as, you may remember that this f was, we could write it as minus L times delta over 4. So it's all of that squared plus, and then the other one was minus M times delta over 4, all that squared. And so the delta itself had an L squared plus M squared in the numerator. So together with that L squared plus M squared, it's going to be an L squared plus M squared cubed. And then there's going to be 4 squareds appearing down here, which will cancel a little bit with that 4 to give us a 4 on the bottom. And then the denominator of the del thing was just this expression that I'm writing down here. nm squared minus 2pl plus ql squared. Yeah, it's delta squared. Exactly. Now it's looking good. And so now when we take the square root If we take the square root of, say, this one or this one, we're going to get this thing here just by itself, and the only irrationality is we're going to have to take a 3/2 of this power of this thing. Same kind of irrationality that we got over there. Okay, so there's something to be said here about what does this term mean? It's clear what L squared plus M squared sort of means. So in terms of the geometry, there's some conic, Z, and it goes to the origin. And at the origin, there is a tangent line, and the tangent line is given by the linear term. So Lx plus My equals 0. And that means that the normal to that tangent line is Lm. Of course, it could be in this direction, we don't know. Now, what's the meaning of this term here? Well, it's interesting. This nm squared minus 2plm plus ql squared is it's a quadratic form evaluated at some vector. So it's the quadratic form. It's clear. It's the that we've been talking about, nqpp, determined by the top quadratic parts of the conic. And the vectors that we're multiplying this thing by are, well, let me write minus m and l. And minus m and l. Where is minus m and l in this picture? It's just a vector lying in the tangent direction, because it's perpendicular to Lm. So here is minus ml. In fact, it's just the rotation of this thing by a quarter turn. So the meaning of this is that we're evaluating this tangent vector at this quadratic form determined by this 2x2 matrix corresponding to the top quadratic terms. It's not an arbitrary thing at all. It's a very pleasant kind of combination. That's the denominator here, and the L squared plus M squared, of course, is just the size of this thing, the quadrants of it. And it's sort of geared so that everything is homogeneous, right? If we scale the whole thing by a factor, then inside here we scale by that square of that factor, and then cubing that's to the 6th power, and down here what's inside gets scaled to the cube power, and we square that, and it's also a factor of 6. So the degrees in the numerator and the denominator match up. So this is really scale invariant, as it has to be if it makes sense. All right, so we are now in a happy position because this is a general conic. And so we can now find curvatures. We can explicitly compute curvatures for general algebraic curves. All right, so now we have this lovely formula for the curvature of a general conic at the origin. So we can now extend this to an algorithm to find the curvature at any point. Oh, let's say x of an algebraic curve W. So here's some curve, it's called W, and here's some point X on it, and we would like to know what's the curvature. So we'd like to find, well, there's the tangent line perhaps, and then some approximating parabola. Or maybe we could use a circle too. Oscillating circle, or we could think in terms of a parabola. And we would like to know what's the curvature at that point. All right, so step 1 is to translate W so that x gets sent to the origin. Okay. That's our familiar story where we consider P of x plus r, y plus s, if x happens to be, say, rs. So we're moving it down, so now this curve has been translated to some new curve, say w prime, and now the new point x prime is the origin. All right, step 2 is to find the tangent conic to w at the origin. And that's now very simple. That's just a case of truncating the expression, truncate the polynomial, just to only leave quadratic terms. And okay, so then we have this, we get this conic, and let's write the conic as Lx plus my plus nx squared plus 2p xy plus qy squared. That's the conic that we're calling w prime. And, well, now we just use that formula. So step 3, just use star to find the quadratic curvature. And if you want, take the square root to find the standard curvature. You'll probably be able to find capital K exactly, but this will involve necessarily an approximation, approximate value. But all right, that's the way it is. How about for finding the evolute? So that's to find the curvature. To find the evolute of the original curve W, we're going down here. We found our tangent conic. We're going to find the focus of the corresponding normal parabola. And I remind you that's our FG. Okay, and how do we do that? Well, what we do is at step 3, what we do is we calculate F, which is FG, by, okay, that was minus L minus M times this delta over 4. Okay, so maybe I should write it out. That's L squared plus M squared divided by 4 times NM squared minus 2PLM plus QL squared. That, not exactly this, but it's this quadratic form evaluated minus ML. Okay, once we've got this, then step 4 is back at x. Here's this focus, let's call it F. There's the vector. So at x we add F, but we actually want to go twice as far. So we go x plus 2F. We might call that C. So C equals x plus 2F. Because remember, the center of curvature is the center of the circle, and that's twice as far away as the focus of the parabola. So we should go twice as far to get to the actual center of curvature. Of course, it's not going to be like this then, and then the circle would be something like this. And that's the center of curvature of the original of W at the point X. And its locus is the evolute of W. And maybe I should just mention, if we want to find, that's to find the evolute, and to find the normal parabola, well, you'd find the normal parabola down here and then translate it up there. So translate, and I'll write down again what the formula for that was: nm squared minus 2plm plus ql squared times lx minus my all squared plus l squared plus m squared squared times lx plus my equals 0. That's the equation of the normal parabola here. So, well, then you'll have to translate that by replacing the x's and the y's with x minus r and y minus s for the original point. So that's kind of a suite of formulas that allow us to very explicitly calculate a lot of things here for a general algebraic curve. Okay, so problem. So this is a little bit of a research topic. It's not too hard, but involves a number of steps. Okay, so the problem is to generalize, or to generalize the treatment that I've just given of a normal parabola from Euclidean geometry to relativistic geometry. Okay, and you can either choose either red or green, or both, if you feel like it. It's probably interesting to do both. So what am I talking about? So let's say that we are working in the red geometry for the sake of argument. Okay? In the red geometry, things are determined by the dot product v1 dot v2 equals x1 y1 times the matrix 1 0 0 minus 1 times x2 y2. Okay, so that's x1 x2 minus y1 y2. That's the dot product. That gives us a notion of perpendicularity. It gives us a notion of quadrants. The quadrants of a vector is v dot v, and vectors are perpendicular precisely when their dot products are 0. Everything with respect to this particular dot product. All right, so can we mimic the story of the parabola in this case? Does it make sense to talk about what a parabola is in a relativistic setting? Well, yes, it does. It does make sense. In fact, we just do exactly the same thing that we've done. But the formulas are a little bit different. And it's instructive to have a look to see what the formulas look like, what the differences are. So what are we saying here? So suppose we have a point FG. We'll start with that same thing. That's going to be the focus. And I better choose a okay, we're doing the red geometry. Maybe I'll put it over here. Okay, in the red geometry, I remind you we have these lines, and like a circle looks something like this. Yeah. And perpendicularity looks like this. Okay, so how can we define a parabola in this context? Well, first we need a directrix. How do we get a directrix? We go an equal amount down here to the point minus FG, minus F minus G. And then we have to choose a line through here, but the line has to be perpendicular to this one. Perpendicular in the red sense, of course. So what's perpendicular to this line? Well, perpendicularity, you can think of it either in terms of tangent to a circle, or you can just think in terms of reflection in the in this line here. So the vector 2, 3 will be perpendicular to the vector 3, 2 in this kind of geometry. Just amounts to switching the x and y coordinates. So the perpendicular to this direction would be in this direction here. That's supposed to be sort of equal spreads. And so that means that if we want a line through here, that we just take something parallel like that. So that's going to be the directrix that we were calling L. So what's the parabola? The parabola is going to be the locus of those x such that this quadrant equals the quadrants from the x to the line. How's that going to be measured? Well, you have to measure perpendicularly. So you have to go in a perpendicular direction, which is going to be the same as this direction, to the line. So you're going to get some foot of the altitude, maybe d. And the crucial quantity is that this and these have to be the same. So it's the same formula. The quadrants of x to f, here was f, has to equal the quadrants of x to the line. All right, so the problem is to work out the theory exactly analogous to what we did in the last lecture in 2, to define curvature just for this parabola, nothing more fancy. Define curvature of this parabola at at 0, 0, and you can try to extend the whole discussion. So once we get this idea, well, then a whole new world opens up for us, because now if we have a general curve, we can ask not just for the standard evolute, that's a Euclidean evolute, but we could ask for a relativistic evolute. We just do exactly the same, but replacing this direction with the actual focus of a relativistic normal parabola at that's tangent here. Okay, I want to do a calculation of an evolute. And curvature, so let's just do a simple example of the parabola. Y equals x squared at some point r squared. And I'm going to treat it as a general algebraic curve, even though, of course, it's a rather special example. So let's think of it as an algebraic curve, so it's defined by as a function of two variables, say x squared minus y. And so if I'm going to go through the algorithm that I suggested, what we should first do is we should translate that. So p of x plus r, and maybe say y plus s, will be x plus r squared minus y plus s. That will be linear terms 2rx minus y plus x squared. This is RS. It's a point on the parabola. The constant terms are going to be 0 because the point's on the parabola. Okay, so this is our L. This is our M. M is minus 1. This is an N. And the P's and the Q's are 0. Just going to apply the formula, various formulas. So the formula for the focus was that we should take minus L and minus M, so minus 2R and 1. And then we should multiply by this this delta on 4. And what was delta? It's L squared plus M squared, so that'll be 4R squared plus 1 divided by 4 times. Now we have to apply minus ML to the minus ML would be 1 R 2RX times the quadratic form, which in this case is just 1, 0, 0. So that's just going to be 1. It's a simple case. So we get, then the curvature is going to be 4 over 1 plus 4R squared cubed. This will be a 1 squared. The little curvature will be 2 over 1 plus 4R squared to the 3/2. And the center of curvature will be, I'll resort now to our form R squared plus 2 times this thing, plus 2F. So that's R squared plus 1/2 of plus 4R squared plus 1 over 2 times minus 2R1. We're adding twice the focus. And when we do that, we get x equals minus 4R cubed and y equals 3R squared plus 1/2. And this defines the evolute in terms of parameter r. And we can get rid of that if we want to by writing something like y minus 1/2, or y equals 1/2 plus 3/4 2x to the 2 over 3 after you get rid of the r's. And the picture that we have is something like this. Our parabola and our evolute, something like that. Okay, so it's obviously interesting fun to try to compute curvatures and evolutes for many classical curves. We'll have all these classical curves, they're just waiting to be analyzed, and basically this is a sure-proof way, very algorithmic, all algebraic. We just compute stuff and hopefully get formulas. But the formulas could be complicated. Okay? And it might be a little bit subtle because you have to use the fact that the point in question is actually on the curve. That might be a little bit of subtlety. So anyway, here's a problem. Try to find the curvature at a point on the Fermat curve x cubed plus y cubed equals 1. And also find, or try to find, some formula for the evolute. All right, so next time we are going to have, now we've got curvature under our belt, we can start looking at all kinds of other interesting things with curvature. So we'll talk more about that next time. See you then.